Then let's continue with transit routers.
Hello again, I guess. So I will be talking about transit router together with my colleague Martin. This is the last talk of the day, so hopefully I won't be boring you too much. So let's get right into it. Yeah, so what we will discuss, just briefly, OVN-IC topology, what it actually means, what the OVN-IC is. Then why do we need something like transit router? Then like demo example of the traffic coming through the transit router, because it's way easier to actually grasp what a transit router represents if we can follow the traffic through the demo topology. And then we will talk about the newer additions, how to configure a transit router from the OVN-IC daemon itself, some demo, and some questions that we would like to hear answers for from the community, if there is something that it might be useful for the use of transit router. Okay, let's get into that. This picture, I was actually told that this picture is pretty terrible, and I can see that it's pretty complicated. But I didn't find a better way how to describe what actually OVN-IC represents. So please bear with me. I will try to describe it quickly and painlessly. So basically, in the regular OVN deployment, we have the regular components. We have our OVN northbound database, OVN southbound database. We have OVN Nord-D that is basically taking configuration from OVN northbound and does some translations, and it will end up in the southbound database, which is then picked up by the OVN controllers. In OVN-IC, what it do, it basically allows us to connect multiple OVN deployments that are independent of each other in any other way. So we have this thing called AZs, availability zones, which basically describes that the OVN deployment. So in this picture, we have two availability zones, AZ1 and AZ2. And as you can see, we have additional components on top of that. So we have two central databases, OVN-IC northbound and OVN-IC southbound. And what basically happens here is that usually the CMS will configure OVN-IC northbound, and then we have OVN-IC process that is running in every AZ that will basically take that configuration from OVN-IC northbound, will do something in it, store some intermediate stuff in the OVN-IC southbound, but it will also program OVN-IC northbound, and it will read stuff from OVN southbound. So this kind of allows us to scale a little better, I would say. This is actually OVNK uses OVN-IC, but not OVN-IC with OVN-IC daemon, which is really confusing because they do it slightly in their own way. But the idea is similar. So it's basically to make it more scalable, and you have a single deployment in OVNK case per node. But this is not like in OVN-IC idea. This is not limited per node. You can have actually multiple controllers that run in each OVN-AZ. So why do we actually need something like transit router? So in OVN-IC, there is a component for a long time called transit switch. What it does is basically this is logical switch that is stretched over the whole cluster like OVN-IC, so over multiple availability zones, which allows you to connect. Basically, this is the way to connect multiple OVN deployments over OVN-IC. But we didn't have anything like a router in OVN-IC because you couldn't do like proper routing over OVN-IC. You would have to do some tricks with a specialized router in each availability zone, and then connect it with transit switch, define routing rules and things like that to achieve basically the same thing. So that's why we said that it might be a good idea to actually do transit router and do it actually inside OVN IC itself. How does it look like? So the transit router is behaving like a regular distributed router in OVN, but it's just stretched over all the availability zones. That's basically all the bread and butter, and that there isn't any magic in that. Yeah, and then this basically allows to simplify the overall topology. So as I was saying, you don't need some extra components and routing rules and things like that to achieve the same thing if you can somehow plug in the transit router. Okay, so let's follow the traffic for a little bit. That might make it a little easier to see what I'm talking about. So this is the topology that I have kind of prepared for you. So we have something external. You can imagine that it's just connection outside into the fabric. We have two AZs, and in each AZ we have gateway router, which is pinned to certain chassis. In each AZ we have pod that is our workload running. This pod is on same layer 2 domain over transit switch. The transit switch is connected to the transit router. Notice there is one important thing. The transit switch is connected over the same IP. So the default route for the pod would be the same in every single AZ. This is kind of important detail in this case. And the transit router is connected to the gateway router. So if we actually want to send some traffic from the external into one of those pods, in this case the pod 20, so we will start at the external. You can see that there is some ICMP, so some ping going on, and we are going from the external IP to the pod IP. What will happen that we will go into AZ1 in this case, into the gateway router. So we will have some, this is the data path flow. It's a little bit shortened. It will enter the gateway router. The gateway router will, in this case, take a look. This is one of those important things. There is a lot of other things happening, but it will take a look into its own routing table, and it will direct it towards the transit router, which is the yellowish color. It should be orange, but yeah, hopefully you can distinguish it from the other yellow that I have put later on. So yeah, it will redirect it towards the transit router and do some stuff like NAT. Here we have SNAT. That's a little trick to make the routing back easier. So the gateway router has a SNAT configured that is its IP towards the transit router. So we will do SNAT for the ping. What will happen next is that we will go through the transit router. The transit router again will do routing, and it will see, okay, I know this subnet. This subnet is the transit switch, so it will send it towards the transit switch. And the transit switch will look up, and from there it's really easy. It will see, okay, yeah, I know that workload. Just send it over to the other side into the other AZ via the remote logical switchboard. You can see it's type remote, and it will send it into the OVN chassis too. And yeah, it will arrive to the pod, and that's one part of the traffic. From the other side, so we will reply that there is a reply for that ping. So we will start at the pod 20. As you can see here, we are sending it actually to the IP address of the gateway router in AZ1. That's the SNAT happening. So yeah, pod 20 will send it, but here is a little catch. The pod 20 will actually send it into the transit router in AZ2, but it arrived from transit switch from AZ1, right? So it will go into the transit router. The transit router will actually see, oh yeah, I know that IP address because it has external connection to AZ1. So it will route it towards TR-AZ1, which is basically the connection between transit router and the gateway, and it will end up on the gateway back in AZ1. And gateway will do again the magic. It will match on the IP address. It will do ANSNAT, and yeah, extra DNAT, and it will send it again into the external. And as you can see, the reply is fine back into the external workload. Here I wanted to highlight what I was talking about. As you can see, the traffic is asymmetrical, but that doesn't matter in this case actually, because the transit router has the limitation of distributed router anyway. So you basically shouldn't use any contract or anything like that, which would matter for the traffic being asymmetrical, right? But in this case, it doesn't. We don't have any CT state on the transit router happening, so it doesn't matter if it's returning back via the transit router when it was the original traffic went into AZ2 via the transit switch. There is one more thing. There is one more catch that we had to solve. So we have ARP learning in regular logical router. So if you send the traffic through logical router, what will happen if the router doesn't know the IP? It will basically ARP for it, which is kind of normal behavior. The problem is that the ARP is happening in ingress pipeline, and with OVN behaves in a way that ingress pipeline is happening before the tunneling, egress is happening after the tunneling. So if we do inside the transit router, if we ARP, we will cross the tunnel and the reply will arrive to the other side, but the other side has the same IP. So we would never learn the ARP response in the AZ that was like sending the ARP in the first place. So that's why we need a thing called ARP flooding for the transit router. What it does, it's basically the transit router has some extra flows that will basically just flood the ARP response to all the AZs. So we inside those AZs, the transit router can actually learn those IP addresses and can have the MAC binding table in southbound populated with the right IP and MAC combination. And I think, yeah, that's about it from me. I'll hand it over to Martin.
Yeah, can you hear me now?
Yeah.
Great, fantastic. Yes, so the transrouter. So here is kind of the list of the commands that we've implemented for the transmitter. Okay, that's better. Great. So the first thing. Challenges. So so at transrouter add. So sorry. So for the transmitter command, so the first thing we had to do was we need to sorry, I'm blanking. Okay, my breath. So the transrouter add. So the first thing we need to do is we need to create a data path key when we do the transrouter add, and that needs to be unique across all availability zones. Luckily, luckily the kind of tunnel key space that we allocate from is that can be kind of sorry. The tunnel key space that we allocate from for transit routers and transit switches comes from this global pool of 64K. So when we allocate from that space, we don't have to worry about having collisions with existing entries in other availability zones. The next step then is to allocate an interconnect southbound data path entry. So each port binding needs exactly one interconnect southbound entry in the interconnect southbound database. So we once we have our unique data path tunnel key, we allocate an entry from that pool. And then finally, once we have our interconnect southbound And finally, once we have our interconnect southbound tunnel key, we can create routers in each availability zone. So here's just kind of the sequence of events. The first thing that happens is when we create a transit router, we will call the OVNIC northbound command, and we'll create a transit. We will asking to create a transit router device there. That will create one entry in the transit router table at the top left there in the interconnect in the interconnect northbound database. Once we have an entry there, the next step then is we need to allocate a data path tunnel key. So so one of the AZs, it doesn't really matter which one, will create a data path tunnel key, and that key will then be inserted into the interconnect southbound database. And finally, then once we have a valid northbound transit router and a key in the interconnect southbound database, the OVNIC process, which you can see at the bottom here in each availability zone, will create a logical router in each availability zone. So here's just kind of the steps quickly. First thing that happens is top left, we create a new entry in the transit router table. Second step then is one of the OVNIC processes, doesn't really matter which one, will take that entry. Then it'll walk through the list of available data path, transit router, and transit switch devices, find the next available tunnel key, and then finally once we have our new tunnel key, we'll create an entry in the OVNIC interconnect southbound DB. Once we have that entry, the OVNIC processes in each availability zone will create a northbound logical router, and we'll set the requested tunnel key for that device to the tunnel key that we added. So so here next is the transit router port add requirements. So the three requirements are first that so right now we're only adding we only create a single entry for the transit router port in the OVNIC southbound database. So we need to decide which availability zone is responsible for creating that entry. Following that, then we need to each availability zone will take that information and create a logical router port in its availability zone, and then finally we sync the tunnel keys across all those availability zones. So here's just kind of stepping through that process. The first thing that happens is we will allocate a tunnel key in the OVNIC northbound, well, not a tunnel key, a port binding key, and we will create that entry in the OVNIC southbound database. Next thing then is the OVNIC process running in each availability zone will take that key and create a logical router port in each of its availability zones. This key then will be matched across all availability zones. And then finally, once we have a unique key in the OVNIC southbound and a transit router port in the interconnect northbound, the OVNIC process will create a logical router port in each availability zone and sync those keys across all of them. And then this kind of just showing the order of steps. First is the interconnect northbound entry, followed by the OVNIC process creating our tunnel keys. Third then is inserting that data, as well, inserting that data in the interconnect southbound, as well as the MAC and other information, chassis, for example. And then last then is we will create just a logical router port in each availability zone, and those ports will have their chassis set to the chassis we provided when we created the transit router port. One kind of important thing to note there is that the port in all but one of these availability zones will have type logical, and in all the others it'll have a remote type. So that's kind of how we connect those various availability zones. The delete requirements. So the transit router port, well, the transit router maintains a list of strong references to all of the ports that are associated with that device. So when we delete a transit router port, all of the resources, the transit router ports, the northbound and southbound database entries, and the tunnel keys associated with that device also get deleted. and we free the tunnel key associated with it. And last thing here is we just have a short demo. So we have a kind of two availability zones set up here, and we have a single chassis in each availability zone, and we're just going to run through the commands to create a transit router, create transit router ports, and then just show the contents of some of the DBs. Quickly. Sorry. Can we pull this video? Just the video here. Yep. Yes. Okay, we're having a few technical difficulties with the video, so I'll just go on to the open-ended questions. So, you know, what we have so far is we can connect the various AZs via ports, but we haven't actually done anything with the routing so far. So I was just hoping we can get some feedback back from the community on, you know, any features that they'd like to, if they're using Transit Router, any features that they would like to have. So we just, you know, we just added some open questions here around, do people have kind of input on routers, some of the routes and how they should be managed across AZs, how they should be synchronized, and finally, and if they had any suggestions around how we should implement local router ports as well. That's it. That's it.
Try the video again.
Again, that's not working.
On your drive, there's a lot of texts. Maybe try again. I mean, I don't know. This is
Sorry, guys.
Okay, then let's continue with questions.
Hello. So my question is about where the data flows. So if you consider two clusters with multiple chassis, would it be possible to have each chassis have a tunnel to the other side of its own, or will everything be centralized?
So two availability zone, multiple chassis, and now you want the traffic to flow between those chassis, or?
Yes, I kind of want to avoid a single bottleneck on either side, if you get what I mean. Like if workload on chassis 1A wants to speak with workload on 2B, I would like the tunnel to go directly and not through like a gateway chassis or something. Is that something we could do?
I mean, that's even possible even without a transit router, because you can connect those workloads with transit switches, right? It's kind of it's a matter of the configuration. It should be achievable even if you choose just the transit switch. That would be for layer 2 domain. But if you want a layer 3 with transit router, it should be also possible. It doesn't have to go. So in the example I have a gateway router for the purpose of the external traffic, but it doesn't have to be that way. If your goal is just to talk between those two chassis and the workloads on those chassis, it doesn't have to go through any central component like the gateway.
Okay. Thank
you. Can you please tell where are the remote ports created? I mean, can we create remote ports on the transit router?
Yes, and that's actually what is happening. So if you create a transit router and you add some port. The port has a chassis specified, and for that chassis it will be local, but we will create kind of clones on every single AZ, and those ports are remote and they represent the port that is local on AZ1, for example, and it's remote on AZ2.
Okay, so with OVN cube IC, right? We could extend the same, have that cluster router have remote ports.
That's actually kind of foreshadowing for tomorrow, because I think Dumitru, Nadia, and Patrick, if I'm not mistaken, will be talking about that. So please wait for tomorrow. They will definitely show some cool tricks how to employ transit router into OVNK.
Sounds good. Thanks.
Yeah, I have like a slight concern about the ARP flooding. Have you tried it on like a more or less large cluster? Like, for example, if you have an OVN IC 500 nodes, it will be broadcasting this ARP to 500 tunnels. I mean, it should be working, but this is going to be executed in user space by OVS, because I'm pretty sure it will overflow the kernel actions limit. So OVS in user space will have to send out all those packets. So I'm just curious if you have some expectations on the performance impact, on if this can halt the cluster practically.
I don't think it would halt the cluster, but yeah, there will be some performance implications, because on the node that will receive the ARP reply, that node will be doing the flooding, so that node will be doing the cloning to all of those. But on those single nodes, it will be just a single packet, because you are receiving just the clone, right? But the one node that is doing the cloning, yeah, there will be some impact, definitely. But we didn't measure anything like on bigger clusters.
Okay, thank you.
I've got the classic question: is it released, or when it will be released?
This is actually released. The transit router portion was in 2503, if I'm not mistaken, and the OVN IC part with all the commands will be in 2603. So I guess partially released. The functionality is there, so you can configure it even without the OVN IC support. But for convenience, OVN IC support will be in 2603.
Follow-up question on Ilyas. So can we avoid that flood? I mean, does OVN IC at the level, does it know the MAC bindings?
So the thing is that if you are running OVN IC, yes, we could extract that from the southbound and synchronize that everywhere. But as we are hinting, in OVNK, that's not the case. They are not running the OVN IC daemon, and for those use cases, it would be harder. So they would need to do it themselves, basically.
Technically add an FDB entry, right? If you add an MAC binding entry, maybe?
Yeah, this would be MAC binding entry, but yeah, this would work. Yeah, you could avoid that, but we did the ARP flooding to make it work, even if you don't do the manual work, basically.
Thank you.
I just assume that if you have OVN IC and OVN cube, can OVN cube synchronize with another OVN cube on a different node? I'm guessing that may be a little bit tricky, but yeah, just comment.
I mean, we're all discussing this now. I can also share my opinion. It's for OVN cube layer 2 networks, where you don't expect to see a lot of ARP replies. So I think it's a valid concern what happens when you get an ARP reply. But in the specific case that transit routers are going to be used in OVN cube, for example, there's not going to be a lot of those. That's connected to the pod network, not to the fabric.
Do we have any more questions? Otherwise, thanks to our speakers.